The next few sections are relativistic momentum, relative velocity in special relativity, and relativistic energy and the equivalence of mass and energy. What I'm going to cover first is the relative velocity in special relativity, and in particular the relativistic addition of velocities. And I'm going to start with an analogy. Okay, so what I'm going to do is imagine that I am adding two slopes. This line, the blue line here, it has a slope, and this line, the red line here, has another slope, and I can adjust those slopes by moving these red dots, or the red dot and the blue dot. Okay, but you can see that when I add this slope to this slope, I get a combination of slopes here. And actually, what I've done is basically taken this blue wedge and just repeated it up here, so that the blue plus the red is equal to the red plus the blue, and the red plus the blue is equal to the blue plus the red. And so wherever I move these two dots, as I move them up and down, the sum of any two adjacent slopes, we're not actually going to be using slope plus slope equals the resulting slope, though, right? Because look, if I'm going to put in here, like say this slope, or this angle, the red angle is 45 degrees, and the blue angle is about 40 degrees. Now, do I get a result of so this ends up being a slope of approximately 1. This ends up being a slope of approximately, or this ends up being a slope of approximately 1. When I add those together, do I get 2? No, actually, I get a delta y over delta x that is very high. In fact, by making both of those 40 degrees, I get rise over run equals 1 divided by 0. So that is an infinite slope. So when I add together two angles, it is not the same as adding together two slopes. Now I'm going to adjust this so that we look at the same situation except with two velocities. Now notice something about these velocities. They are constrained so that you can only go from 0 to 1. You can't go past that. But there's a similar phenomenon going on here, that the red area plus the blue area here is equal to the red area plus the blue area here, and that red area plus blue area is equal to this blue area plus red area. So what happens is that you can basically take the velocity formulas, convert them to rapidities, add together the rapidities, and then convert back to velocity. So this can actually be written, I've kind of written this in several ways, maybe too many ways, but basically your first velocity is c times the hyperbolic tangent of that rapidity. Your second velocity is c times the hyperbolic tangent of the other rapidity. And we can basically take those two rapidities, add them together, and get the final velocity is c times the hyperbolic tangent of the sum of the rapidities. You can also take each of those rapidities, phi1 and phi2 is arctangent of v1 over c and arctangent of v2 over c. So you can write it that way. The way they express it in the textbook is this way: v1 plus v2 over 1 minus v1 v2 over c squared. This is essentially the hyperbolic, or this is the hyperbolic angle addition formula. Basically, except for the extra presence of the c here, it's a tangent phi1 plus tangent phi2 over 1 minus tanh phi1 tanh phi2. Let me write that so that we have the hyperbolic tangent formula, or hyperbolic tangent addition formula, all on one line. And you can see that the hyperbolic tanh formula is the same as this equation down here. Now I've made this kind of weird notational change down here. See, notice here I'm saying beta 1 is V1 over C, beta 2 is V2 over C. So I'm going to multiply both of those, C, by beta 1 over C plus beta 2 over C to get V1 plus V2. But I'm using this weird symbol here. It's a big O plus, but it's not exactly addition. This symbol represents addition, this symbol represents subtraction. Everything here is plus or minus. The only thing that is not a real arithmetical plus is this thing right here, because we're changing the definition from this, because this operation over here, what you're doing to beta 1 plus beta 2, is definitely not the same as arithmetical addition. Okay, so for now I'm done talking about the velocity addition formula. I want to kind of introduce this topic. I don't know if I'm going to get to the whole derivation in this video, but I might get to it tomorrow. We're going to accept this equation as given. Momentum, the relativistic momentum equation, is mv over the square root of 1 minus v squared over c squared. Alright, this formula can be expressed as p equals mc times the hyperbolic sign of the rapidity. And I'm going to use that because I'm just going to take that part as given, and I'm going to do this gigantic formula. Parts 1, equation 15 here goes through steps A through I. Equation 16 goes through steps A through G, and then equation 17 goes from steps A through J. And at the end of this, we will have essentially E equals mc squared, but more E equals mc, or the kinetic energy is mc squared times cosh phi minus 1. And actually that is this equation right here. Kinetic energy equals gamma, that would be our cosh phi right there, mc squared, minus mc squared, that would be our minus 1, gamma minus 1 times mc squared. So I'm going to provide the derivation of that, and it begins with this equation 15, where we take the derivative of the arctangent. And the derivative of the arctangent is basically phi is the arctangent of beta. So we want the derivative of the arctangent of beta, and it turns out it's cosh squared of phi. You can follow along that to get that that fact. Then when we find out what the relativistic force on something is, we use this equation that force is the change in momentum over time. We plug in our equation for momentum, mc sinh phi, and do the derivative, and at some point in here we're applying that d phi d beta that we just calculated, d phi d beta, which took a lot of work to find, but now that we've got it, we can stick in that it is cosh squared, and this leads us to a cosh cubed, and that gives us gamma cubed times mass times acceleration. Then I have some description of exactly how each step is done. And then I have finally the relativistic kinetic energy, which is work equals the integral of the force times the distance. We're using that force that we just calculated, gamma cubed mc del beta del t. C times del beta del t is our acceleration, So basically we go through a bunch of steps here until we finally come up to an integral, and we get cosh phi minus 1 for the work done to accelerate the particle from 0 to a final velocity is going to be equal to mc squared cosh phi minus 1. Now, the step here with the approximately equal sign, step J, is converting that from the exact relativistic expression to the approximate one half mv squared that you're accustomed to. Let me make one other thing, kind of an item of interest here before I wrap up for today. I think it's interesting that in this equation, kinetic energy does not actually appear. This equation that says E squared equals PC squared plus MC squared squared. This term here is E squared. It's MC squared cosh phi squared. This term here is PC squared, so it's MC squared sinh phi squared. And then this term here is just plus MC squared. So basically, this equation, we can pull out the MC squareds, or divide everything out by the MC squared squareds, and we end up with cosh squared phi equals sinh squared phi plus 1. It's just that equation multiplied by MC squared. So, but the kinetic energy is MC squared times cosh phi minus 1. So none of these terms up here, this is not the kinetic energy, this is not the kinetic energy, this is not the kinetic energy. The kinetic energy is MC squared cosh phi minus 1. The rest mass energy is in there, MC squared, which is kind of associated with that minus 1, I guess. So if we were to draw this diagram with using hyperbolas, you can kind of think of this part of the shape being MC squared, the whole shape here being MC squared cosh phi. This here is the kinetic energy, right in here, right here. That's the kinetic energy, MC squared times cosh phi minus 1, where this is the rest mass energy. And over here is the MC squared sinh phi, that's c momentum times the speed of light. Try to show that one more time. The rest mass energy is from here to here, and the kinetic energy is from here to here. The total energy is the length of this line here, and the momentum times the speed of light is the length of this line here. And now I have the diagram looking just right, with momentum times the speed of light on this axis, and the rest mass energy, kinetic energy, and the total energy all labeled in good spots. Now you can mess it up completely by moving this dot. Blah, blah. Yeah, moving the dot messes it up. But if you get that up there right, it looks nice.